I'm really happy to have you here, Chiara. Chiara Marletto is a researcher at the physics department of the University of Oxford, and she will speak to us today about constructor theory, or as she calls it, the science of can and can't, which is also the title of the book that is coming out, I think, in next spring, if I'm correct. Yeah. And I contacted Chiara after our previous Foresight Salon on quantum computing with Scott Aronson. And while I don't pretend to fully understand your theory, and I definitely won't attempt to try to describe it here in the introduction, I'm really looking forward to your talk. I will post the description of both your talk and a little bit more intro about you in the chat here. And then I would say we leave the questions for the discussions. People can just mark them with a Q, and I'll explain all of that again in the chat. And yeah, I would say take it away, and I will moderate in the chat everything that I won't take much more space in doing here. So, but welcome. I'm really happy you made it, and I can't wait for the presentation.
Yeah, thank you very much. This is a great opportunity. I enjoy this the possibility of talking in this context. Is a great initiative. And so I will probably share my screen, and I'll try to talk you through the basics of this new theory. And of course, this is a very short introduction. So hopefully, because this should be a very interactive session, I'm very happy to have more questions afterwards. So I'll keep it short, and then I'll open to questions, and I'm hoping to have a nice conversation with you guys. So the best way to understand, I think, constructor theory is to start with something that's possibly well known, let's say, at least the name is now quite present in the news, which is quantum computation or quantum computing. And the way I like to start these kind of discussions is by reminding ourselves what quantum computation really is. And I think, if Scott Aronson was here at some point discussing about this, you probably got the gist of it quite nicely from him. But I guess what I want to say here is that the theory of quantum computation is a very interesting place from the conceptual point of view, because it's a place where technology, so applications and things that can have an impact on the life of people in everyday life, meet the foundations of physics. And this is very rare, because usually you have these very abstract theories of physics that seem quite distant from what we do in our everyday lives, and then we have applications that can come out of those. For example, GPS coming out of general relativity, but this only happens after a long time since the proposal of the theory. Whereas in the case of quantum computing, I think the theoretical ideas were proposed in the 80s, and then it was immediately clear that this theory would, on the one hand, deliver lots of applications, so things like quantum cryptography and quantum algorithms can run on this universal quantum computer, but also would allow us to understand quantum theory, which is one of the most fundamental theories of physics we have at present, much better than we did at the start. So I think there are some issues at the basics of the foundations of quantum theory which were still to be uncovered in the 80s. And I think now we understand them much better thanks to quantum information. Now, the interesting thing about quantum computing is that, on the one hand, there are lots of technological efforts going on at the moment to create this universal quantum computer, which will replace the objects that we currently use as our personal computers. But there is another interesting thing, and this is the fact that conceptually, quantum computation in itself, if you look at it from the point of view of fundamental physics, is an unfinished revolution. So something is still to be done in order to complete this conceptual revolution that was started in the 80s. And this has impacts both on theoretical physics, but also on computer science and also on technology. And constructor theory is connected to the way in which I imagine this revolution can be completed. So let's see why I say that quantum computation is an unfinished revolution. So when you open a book about quantum computing, I mean, might happen if you're not a specialist, it could be a bit of an exotic experience, but I think you can try. And what you'll see is a lot of equations that are based on the dynamical equations of quantum theory. So the things that Schrödinger and Dirac and Einstein and people like that came up with at the start of the past century are the very same equations, rules that are being used in order to power the theory of quantum computation. And this is a bit weird because you would expect quantum computing being all about information and things that are more general than just a specific physical theory. You would expect it to be expressed in more general terms. And it's not just an expectation that one has, an intuition. This is actually an expectation that comes from the fact that in physics, we physicists know that our theories, even our best theories like quantum theory nowadays, or general relativity, or Newton's laws, for example, in the past, are bound to be changed because they are, let's say, the current best guesses to understand the universe, but they might be wrong and they might have to be modified. So in fact, most physicists expect quantum theory to be changed at some point in view of the fact that at present it doesn't quite accommodate a very important phenomenon of our universe, which is gravity. And of course, Einstein there reminds us of the fact that gravity is well described within physics by a theory, which is general relativity. But that theory doesn't quite go together with quantum theory. So that's why we actually expect both theories to be changed. So from the point of view of quantum computing, this is a bit worrying because if our understanding of quantum computing is really only based on quantum theory's dynamical laws, and if at some point these laws will be changed, so then the question is quantum computing still going to survive then? So one question through which we can try to go beyond quantum computing as we know it right now is, can we find a way of formulating quantum information theory or quantum computation theory in a way that doesn't rely fully on the apparatus of this theory of physics as we call quantum theory? So how do we go beyond the dynamical laws of quantum theory and still retain or improve actually on our understanding of quantum computation? So that's the first question. There's also another sense in which quantum computing is not the whole story. Is not that there's something beyond the universal quantum computer, and this is the title of this slide. So it's the fact that despite the name, when you think of a universal computer, you're not referring to the most universal machine that one can conceive of. And here we need to have a little thought about this. So a universal computer is a machine, a computer that can perform all computations that are physically allowed, computations. And this is something that Turing and then Deutsch and also other pioneers understood very well when they approached this concept within their own respective fields. But there are some tasks, some processes or transformations that the universal computer, classical or quantum, cannot perform. So there are things that go beyond the capabilities of this machine. And the most important one, which is interesting for us for various reasons, is the task of creating a replica of oneself. So when you think of, let's say, the task of reproducing a cell. So you got a cell, the cell is self-reproducing, is creating a new instance of itself, a new replica from raw materials. That task is actually seems very straightforward from the point of view of biology, but turns out that a machine like a universal computer, although it can be programmed to simulate that behavior within its workspace, it cannot itself create a new instance of itself. So, you imagine you could program your Mac or your PC to assemble a new computer out of raw materials. That's not possible. It's just not something that a computer is designed to do. And yet it's a physical process. It's possible. It's allowed by the laws of physics. So this tells us that there is a more universal machine than a universal computer. So that's why we need to upgrade quantum computing to include these machines as well. And these machines are called universal constructors. So this is an idea that John von Neumann, polymath, great physicist and mathematician, already understood in the 50s, even before the discovery of DNA. So this was quite cool. So he understood completely the logic of self-reproduction. And in that context, he defined this idea of a universal constructor, which is a machine that can be programmed to perform any task or any physical transformation that is physically allowed. So if you don't want to go into the details of this definition, you can just think of it as a universal 3D printer, in the sense that it's an object that you load with a program describing what you want to be built, and so long that the thing you're writing in the program is allowed by the laws of physics, whatever object you're considering, with the right program, this machine will assemble it for you, given enough raw materials. And we don't have a theory for this machine. So we know we can define it, in principle, but we don't have a theory that explains to us what are the physical limitations of this machine, under what conditions these machines can be built, and so on. And that's the second sense in which the theory of quantum computing should be generalized, because you would like to have a theory of quantum constructors, of universal quantum constructors, that are like the upgraded version of universal quantum computers. And why is this exciting? Well, it's exciting because we already know that the universal quantum computer is bringing us very close to possibilities that we couldn't even imagine just with classical machines, with classical computers. And the theory of the universal constructor, even though it could be very far in the future, could be bringing about the next technological revolution, which could be comparable to the IT revolution that we've had just now. So let me try to explain now the logic of how one could answer these two questions. So we got two questions. Questions are good in physics because, in fact, in science in general, or even in philosophy, the questions are actually problems. And these problems are interesting because they tell us that despite the success of quantum computing, there is a lot more to be done and to be understood further than that. And so one can think of ways of answering these two questions. So how do we generalize quantum information so that it becomes independent of quantum theory, and also it can include machines that are more general than quantum computers? And the answer, surprisingly, comes from, well, maybe not so surprisingly, comes from taking a look at how physics formulates explanations. And I think, so this is the second part of the short presentation, where I'm telling you where the gist of the answer to these questions comes from. So, as I said, I think physics can be considered as a collection of guesses about how the universe works in its most fundamental ways. And I think we really only have a handful of good guesses, laws that work as rules that are good for making predictions, and also are not just rules for making predictions, but they provide satisfactory, unproblematic explanations of physical reality. And these laws are written here in part. So we've got Newton's laws, Maxwell's equations, and this is the classical part of physics. And then we have the recent theories, general relativity and quantum theory, that, as I said, were discovered at the start of the last century. And so together, all of these laws are the best guesses we've had so far as far as the, guessing how objects move in space-time is concerned. And there is one trait, so all of these laws look very different, but there is one specific thing that they have in common and that makes them very similar to one another. And it's the fact that they all rely on a specific way of formulating predictions, which is that they, a bit like in this little cartoon over here, they are based on dynamical laws. And dynamical law is like a description of the set of points in space or in space-time that an object goes through, given some initial conditions. And I think even though in this case we're only looking at a football being kicked inside the goal, and of course you can use Newton's laws to describe the football, but you can also describe this through general relativity and quantum theory, and you will get the same predictions at this scale. These laws are very general, so you can do this for this specific example, but you could do it for the whole universe. And in fact, the goal of fundamental physics formulated in this way is to really give just the trajectory of all particles that constitute the universe. And once you've given that and the initial conditions, you've explained, well, let's say, most things that are to be explained. So that's the kind of logic behind this way of looking at the world. However, there are other ways of expressing physics. And I think you must know about these things because they are everywhere in let's say, in thermodynamics and in other branches of physics that we've all somehow met one way or another. And I've written here 3 examples of these other kinds of laws that I want to call physical principles. These 3 examples are very famous in some sense. So maybe the first 2 are more known. So you see on the left this conservation of energy, which says that the energy of an isolated system can't change. So if energy changes somewhere in the universe, there must be somewhere else in the universe where the energy is changing in such a way that the first change is compensated. So there is a sense in which overall the total energy of the universe has to be conserved. And this also implies that you can't build a perpetual motion machine of the first kind, which is supposed to be, this is an example of an impossible motion, the thing I represented here on the left. And so the conservation of energy basically says that certain transformations are impossible. Specifically, it's impossible to build a perpetual motion machine of the first kind. And the second law of thermodynamics, which is the one in the middle here, also says that some transformations are impossible. So it says that you can't turn heat completely into useful work with no other side effects. If you could, then you could use, let's say, the thermal energy of the sea in order to power a boat and make it proceed through the waves. And of course, we know that can be done. And this is not just an accident, it can't be done because there's a law that says it can't be done, and that's the second law. And the third law that I reported there, which is actually not a law about impossibility, but it's about possibility, is the computability of nature, which says that a universal computer is possible. And there's a question mark there because we really don't know, although the first 2 laws are well established, the third one is a bit controversial or unsettled yet. But I think it's interesting that it's formulated in terms of a statement about what is possible. And so this is declaring that a certain transformation can be done. And there, for your amusement, I I put this nice cartoon, which comes from an illustrated story about the first attempt to create a universal computer, which dates back to the Victorian era. And this is Charles Babbage, this guy over here. He was a scientist in the UK who devised this machine called the analytical engine, which the whole of it actually should have worked just like a computer does. So it would have been the first programmable computer available to humanity. And then here is Ada Lovelace, who was his collaborator, and she was the first to understand that this machine, this universal computer, could actually be used not just to compute, to churn out numbers, but to do many more general things. And I think she was even thinking of using it to produce music or poetry and so on. So I think two of them really pioneered the idea of the computability of nature, the fact that a universal computer is possible. It's a shame that they couldn't build a computer, lack of funding. These problems are present now as then. But I think it's very remarkable that they had this intuition. So anyway, to go back to our point, the gist of this slide is that the principles that are in physics, such as these ones, are not about dynamics. So there are no dynamical laws, not like in the case of Newton's laws, but they are statements about possible and impossible transformations. So they say some transformations can be done and others can't. And so here comes the intuition. So is it possible, in order to answer the questions that we started with about generalizing quantum computing, is it possible to take inspiration from these kind of laws, the principles about possible and impossible transformations that already exist in physics, and generalize them and formulate the whole of physics in terms of these statements? Is that going to give us, as a byproduct, also a generalization of the theory of computation? It sounds like a crazy idea, but that is what constructor theory is about. And the idea is not so crazy if you look at it very carefully. So, so here is how I introduce now constructor theory's program. So this is a program it's a long-term program for a scientific project that can be developed in the future. So the idea is that instead of defining physical laws in terms of dynamics, so like instead of using Schrödinger's equation or Newton's laws or Einstein's equation and so on, you take laws about that are expressed as statements about tasks being possible or impossible. And then, so generalizing these principles that I just mentioned. And then you try to derive dynamics and initial conditions from these statements as emergent consequences of the principles. So you're somehow switching the standard way of looking at the standard way of formulating laws of physics, which is in terms of dynamics. And you're trying to put the statements about possible and impossible transformations at the foundations, and then you derive the statements about dynamical laws as a consequence of those other statements. And this is, so it's very interesting that if you do this, you also solve the problem about generalizing quantum computing, because what you get out of this procedure is automatically a generalization of quantum computing to general tasks. And this is actually what provides the theory of the universal constructor. So following the constructor theory's program in this way also delivers a potential answer to the questions that I presented at the start. So let's see, to summarize, let's say what the two roles the constructor theory is expected to play. And I think my work and David's work in this field and the work of our collaborators shows that these two, that this is actually happening. So this is quite exciting because it's something that's happening right now. So on the one hand, you see that constructor theory is a candidate to expand on the theory of computation in the two ways that I said. So because it doesn't rely on dynamical laws, but only uses statements about possible and impossible tasks, it automatically, doesn't rely on quantum theory. So it allows us to generalize the quantum theory of computation to a domain where quantum theory may not hold anymore. And we hope that this is going to be the basis for delivering the theory of the universal constructor. And ultimately, once you have a theory of the universal constructor, you will also be able to construct a universal constructor. So that's let's say the very, very long-term goal that we have with this theory. And at the same time, the interesting thing for let's say from the physics point of view is that the theory, constructor theory, has this novel physical principles that generalize the existing principles that we have in physics, such as those that I mentioned to you earlier. And these nice principles of constructor theory have a very interesting feature. So they are general, so they can apply to systems that don't necessarily obey the current dynamical laws that we know. And the chief physical system that comes to mind when you talk to a physicist about this issue is quantum gravity. So as I said earlier, gravity is this weird entity that is very well described by the theory of relativity, but unfortunately it doesn't quite fit with quantum theory. So if you have an object which is a hybrid object that involves both quantum effects and gravity, you can't use either of the theories. You can't use Einstein's theory and you can't use quantum theory. But you can use constructor theory's principles. And this is very promising. And let's say this is the second way in which constructor theory can deliver to us very interesting results, because it allows us to go and probe areas where current dynamical laws are not directly applicable. And so to end on a positive note, this is a recent application of this logic, which was very exciting to the physics community. You can explain how to test non-classical effects in gravity by using only constructor theoretic principles. And this is very nice because I would say it's the first application of constructor theory that connects these general principles with the experiment. And so I think on this note, I'll just end this short presentation, and I'm very happy to continue the discussion with you when I kind of stop the share. Thank you for listening.
Thank you so much. Amazing. Okay, very understandable too. Well done on that. I already see, I guess, already 5 questions collected in the chat. So this is for me an invitation to everyone who would like to join the queue and ask a question, to just preface your question with a Q in the chat. And we'll start right off the bat with Tad Hawk, and I'll unmute you if you don't mind. Hi, and Ted.
Okay, yeah, thank you.
Ted, perhaps you can also say a few words, just your background, if it's relevant.
Sure. So my name is Tad Hogue. I'm a physicist by background and done some work on quantum computing algorithms, and have been involved with Foresight and molecular machines for many years. So my question is that you at the very beginning you talked about the conflict, so to speak, between quantum mechanics and general relativity, and the need eventually for a better, more complete theory. But also physics has this notion, what's called an effective theory, that quantum mechanics works perfectly well at sort of everyday scales, and gravity's not so big and so not so strong and so on. So in terms of a theory of computation, isn't what we already have with quantum mechanics for sort of everyday Earth-based computing likely to be perfectly sufficient in terms of what a computer that we could build on Earth could ever do?
Yes, so this is an interesting question that, so I think it's got 2 answers. One is more foundational, and the other one is maybe more on the practical side. So I prefer the foundational one. So
those are the more fun ones, yeah.
Yes. So in a sense, you're right that one could have a pragmatic take on things and say, well, as you said, if quantum theory is effective at least at the scales where we are expecting to be able to build computing machines, then why worrying about other effects and incorporating more general theories and so on. So I think that the foundational answer to this is that when you're thinking of, as a purist, to a theory of information, and you look at the classical theory of information that, let's say, on which Shannon and other things are, I mean, Shannon's theory and the classical theory of computation are based, you see that the dynamical laws of classical physics feature very little. And it's the theorems and the statements are made in very general terms. So they're made in terms of distinguishable states and permutations of those states. And then, there are some results about channel capacity and so on. But when you switch to quantum computing, on the other hand, as I said, when you open a book about quantum computing, it's really quantum theory dressed in some computer science language. And being a physicist, I'm very happy about that. I quite like that. Mm-hmm. But on the other hand, if I look at this from the information theoretic point of view, it would be much better to have a theory that's only expressed in terms of information theoretic concepts. So, for example, when you talk about entanglement, or when you talk about the quantum advantage that comes with a certain algorithm, it would be nice to be able to explain in what sense just in terms of information theoretic concepts, why these things are different from the classical counterparts. And the only way in which you can do this at this stage, I think, is to just run certain dynamical processes with unitary transformations or CP maps or whatever. And then out of that, you can distill some kind of comparison. But it's very odd from the point of view of the foundations of information theory. And so this is a foundational answer. It would be nice to have a unified way of treating classical and quantum information in this general framework. The other answer, which is more practical, is that there are very sensitive clocks that currently are being built, which allow you to detect effects like the gravitational redshift and related effects already with very tiny masses. And so in a sense, quantum phases that could be used to perform quantum computations can be affected by gravity. And there have been a number of experiments, even though, still much has to be done. And so in a sense, I think I'm not so sure if it's so true that quantum computers can't be built at the scales where gravity is important. It's true that you want probe gravity where maybe GR is fully effective, but there is still a point where you have to reconcile this fact that you've got a mass in a superposition of different locations, even tiny mass. Mm-hmm. And then you've got to think, what does the gravitational field do at that point? And as we know, Einstein's theory suggests that the gravitational field is classical, so it cannot be in quantum superpositions. And so how do you describe that? Even from the point of view of quantum computing, let's say you're using a tiny atom to perform a quantum computation, that atom has a mass and it gravitates. So
those are really interesting questions. Yeah, thank you.
Thanks for the question.
All right, thank you. Okay, next one up, we have Alyssa's question. Alyssa, I'll unmute you.
Hey, can you hear me?
Yes.
Yeah.
Perhaps you could also say 1 or 2 words about your background, just that Chiara hasn't, if you want to.
Sure. So my name is Alyssa Vance. I'm a senior core technology engineer here at MCD Tech Labs, where we are building a dialogue conversational AI for the McDonald's drive-thru. Yes. So question, when you talked about limitations on classical computers, like classical computers can't build copies of themselves, are you referring to like engineering limitations that we have like, in the year 2020, or are you referring to like some sort of more general or more theoretical limitation? Because we have one kind of of limit where we know that computers will never be able to solve the halting problem, or there's a generalization called Rice's theorem where it's just like, computers cannot do this ever. And then we have things like, it's in the year 2020, Homo sapiens sapiens has not yet figured out how to do this, but it may still be possible in the future. Right now, you can't do more than 10 to the 13th computations per second per chip or something like that. But that's not an inherent limitation. That's just sort of like an engineering limit. So could you clarify what you meant by that?
Yeah, this is a great question. I like it very much because I'm always, in theoretical physics, you're very interested in the foundational limitations. So not the one that's due to the lack of, creativity or lack of inventiveness or lack of money. But I think what we are interested in is really whether there is a fundamental limitation that really can't be overcome. No matter how hard you try, you can't do a certain thing. And in this case, I think von Neumann was really referring to this logical impossibility. So so if you think of the architecture of a Turing machine just has its workspace, which is a tape. And so all the outputs that the Turing machine is supposed to produce are confined to that tape. So it's logically impossible for the Turing machine to also construct the rest of itself. So it can only operate on this tape. But in order to create a copy of itself, it should be able to operate on the other part that's not the tape, because it should be able to copy in some way the full of its architecture into, let's say, a bunch of raw materials that are kind of floating about. And that cannot logically happen. It can simulate the self, reproduction of a cell by suitable program. Of course, cellular automata are all about that. But here is the question of whether it can create a copy of itself with a suitable instruction. And the von Neumann machine, or more generally, the universal constructor, has this feature. So it is a programmable machine that can perform any task that's physically possible. And so if you assume that machine is possible itself, then it must be possible to create a new instance of the machine itself. So I think that's why the universal constructor is really represents a new class of machines that go beyond Turing machines, because they can operate on other things than just bits confined to a tape. So in a way, it's a fundamental limitation. And I like your question very much. I think it's a great question. Yeah.
Thank you.
Thanks.
All right. Thank you so much. Next one up, we have Rowley. And Rowley, I hope I'm not I'm not catching you off guard, and I'm muting you right now. Rowley, perhaps you could also say a word or two about your background and then your question.
Hello there.
Hello.
Cool. Hi. So my background is I'm interested in philosophy, and so I've done my studies in philosophy, and that just kind of because I don't know about this constructor theory, this new stuff for me, and I just kind of that comment caught my eye with the idea of nature being the computability of nature.
Yes.
So is that to what extent is that to say that is that the question of, is nature fundamentally mathematical somehow, or is this an ontological question, or more like an it's a huge ontological question in philosophy in a way.
Yes.
Is there some is that the sort of strong sense in which you're suggesting that here now, or?
Yes, I think this is a very nice question, because it touches on a subtle issue that sometimes causes some confusion as well in different fields. So so when let's say in quantum computing, or at least in physics, we think of computations, what we mean is is some kind of function or permutation or transformation, more generally, of a bunch of input states in a bunch of output states. And the additional thing that we want for this to be a computation acting on information degrees of freedom is that the input states are all somehow distinguishable from one another. But just to answer your question, I think the computability of nature says something very specific once you have decided that this is your notion of computation. It says this, that if there exists a computer, a machine that when given specific inputs can perform one type of computation, let's say addition, and if physically, I'm now thinking, when I say it exists, I mean it exists given the laws of physics that we know. And if there is another machine, if another machine is allowed, which let's say perform another computation, for example, multiplication, then there must exist also a more general machine that can perform either of those given a suitable program. So you can think of a more general machine that when you say, I want these two numbers to be multiplied, performs multiplication. And when you say, I want them to be added, it will perform addition. This means physically that you can compose these, computing machines in very specific ways. And it's an accident of the laws of physics that we know. You can prove this through, with a theorem within quantum theory and within a discretized version of Newton's laws, that they have this property. But it need not be. So there could be other models where you've got lots of tiny computing machines that can perform specific tasks. But if you want a universal computer, one like the one that we are using now, you can't build one. So at some point, you can't compose together further, all of these special purpose computing machines. So the computability of nature is a kind of technical term, I suppose, that I was using to refer to this specific property. And now then there are these other, so there's a theory of computable functions in mathematics and so on, which refers to a specific model of computation, which is Turing's model, and etc. And that's a different thing. So I was trying to be more general in the sense that this computability of nature can be really defined under any model, so long as you have, let's say, some dynamical laws that tell you what are the processes that are allowed. I hope that makes sense.
Yes.
Cool.
Awesome. Thank you so much. Next one up, we have Mike.
Hi, this is Mike. My background's mechanical engineering, design, and also did computer IT service. Yeah. So I just want to comment. Part of it sounds like the problem of the origins of life in a way that we know how to create the primordial soup and chemicals, but we don't know how it actually starts as a self-replicating life. So this constructor theory kind of reminds me of the same kind of situation. Just an observation, but my question was, if you've looked at all at category theory and applied that to this constructor theory as a way to deduce what principles and laws there might be based on your observations.
Yeah, that's a nice question. I think the category theory is this very powerful mathematical tool that somehow powerfully generalizes set theory and kind of upgrades it in a dramatic way. And I think although at the current stage, so constructor theory is formulated more in the context of set theory, but I think one of the students that's working with me, he's interested in translating the current results of constructor theory within category theory, because that appears to be the most natural language. So I like your question because it's somewhat related to a current development in my own research with this collaborator of mine. And I think it's very important to express the theory in more effective mathematical ways, because, of course, once you do that, then you can see even more connections that you maybe wouldn't otherwise be able to see. And about the origin of life comment, I think the concept of a constructor is possibly, I think it is related to life in some sense, in the sense that I didn't go into these details, but I think what von Neumann called the constructor is generalized in physics and in biology with anything that can effect the transformation on a physical system and stays unchanged in its ability to cause this transformation again. So it's something that works in a cycle. And so obviously cells and organisms have this property. But the interesting thing about constructor theory is that we are trying to, so despite being called constructor theory, it's a bit like with relativity. The theory is not about constructors. Constructors are the things that you abstract away from the description, because all the laws are about possible and impossible tasks. And a task is possible if you have, if there can be a constructor that performs it. And it's impossible if there cannot be one. And so by restricting your statements to whether a task is possible or impossible, you are avoiding the issue of enumerating the constructors, saying where they come from and how they have to be constructed. So in a way, you are abstracting away the issue of where do the constructors come from. But I think you're right that there is a strong connection with biology, at least at the conceptual level, when you're talking about constructors. And von Neumann was motivated by biology when he made these remarks about the universal constructor, because he was trying to understand how life fits into the laws of physics, which of course it does. But I think at the time it wasn't quite clear because we didn't know about DNA yet and things like that. So, yeah.
Anyway, thanks. Great. Yeah, I was just, polymerase and DNA looks so much like a Turing machine, the way it operates. So,
Indeed, yeah. Yes, absolutely.
Yeah, well, thanks a lot.
Thank you.
All right, lovely. Okay, next one up, we have Logan.
Hi, I'm Logan. I'm a science writer. Hello. So you said in your talk that you hope to maybe deduce the boundary conditions from these constructor theoretic principles. So I'm guessing that includes, let's say, the initial state of the universe, hopefully. But do you think constructor theory has anything to say about maybe the final state of the universe if people don't intervene between now and then, for example?
Yes, I think the program, so that part of the program hasn't been, so we haven't realized it yet, but I think the expectation is exactly as you were saying, to once you lay out all of these statements about possible and impossible transformations, you can find ways of showing which dynamical laws and which initial conditions or boundary conditions are compatible with those statements. So in a sense, because of one would expect that the dynamical laws that are compatible with the principles are of the form that we know already now. So for instance, general relativity and quantum theory should be compatible with constructor theory's principle, and we know quantum theory is compatible and general relativity also most likely is. So because those laws are time reverse symmetric, so that means that they are the same, whether, when you're evolving them from past to future, they are the same as from future to past. Once you make statements about the initial conditions, the same statements should be possible to make about the final conditions. So because of the symmetry of the laws, I would expect that once, if you manage to say something about the initial conditions of the universe, you should be able to say something about the final conditions. So hopefully, yes. The answer is yes to what you asked. But of course, we have to do it. Yeah. Thanks for the question. Thank you.
All right, we are making progress on the questions. So if there's others that still want to collect theirs, we may even get to them. So let's see. Next one up, we have Jesse Nichols. I will unmute you now.
Hey, so I was wondering about the rationale or epistemology that this work comes from. I ask because I know the context of this organization's a bit on the more Bayesian side. So I wondered, how does this theory deal with credences or probabilities?
Yeah, that's a great question. So I think in a way, these questions are more at the meta level. So it's a bit like the same question could be asked about current dynamical laws, right? So quantum theory or Newton's laws and so on. And for all laws, including I think constructor theory, for all laws we know right now, the deterministic structure comes first. So if you think of all these laws that we have, so there's Newton laws, Maxwell's equations, quantum theory, and general relativity. And in all those cases, you have a dynamical transformation which is deterministic. So, in Newton's laws, you know what the dynamical laws are. And then in quantum theory, Schrödinger's equation is also deterministic in the sense that it evolves this quantum state deterministically from one time to another, and so on. In quantum theory, there is a bit of a complication because when you make a measurement on the quantum state, then there is a probabilistic outcome. But if you describe everything from the point of view of the whole universe, and if you believe that quantum theory applies at the level of the whole universe, which is what quantum theory seems to say, then the whole universe is evolving really deterministically, and the appearance of stochasticity is really only to do with the measurement events. So overall, it's all deterministic. And likewise, I think in constructor theory, the fundamental statements are deterministic. So when we say a task is possible or impossible, there is no probability involved in that statement. However, you can accommodate or derive probability within from those statements. So you have some axioms that don't involve probabilities, but you can derive the certain probabilistic statement out of those axioms, just like in quantum theory. And so this is as far as probability are concerned. For credences, this is even more abstract because this refers, let's say, to a certain theory of confirmation of science, of, let's say, theory of confirmation within scientific method. And I think constructor theory is agnostic about that in a way. So if you approach theory confirmation from the Bayesian point of view, you will be able to apply it to constructor theory as much as you can with other physical theories that we have at the moment. And then I'm happy to discuss about Bayesianism as well. I mean, my inclination is that I tend to think of things in a more Popperian way. So I think Bayesianism maybe is not so necessary. But I don't think it would, if you're a Bayesian, yeah, exactly. If you're a Bayesian, I think you can still, take the whole constructor theory and make sense of it, just like you would with another physical theory. But, if you ask him about my own bias, I think I tend to think that Bayesianism is not completely adequate to explain theory confirmation and sometimes a bit misleading.
Thank you.
I hope that answered the question. Yeah, cool.
Awesome. Thank you so much. Next one up, we have Dennis. Dennis on you.
Hey, can you hear me?
Yeah.
Great. Hi, a great talk. Nice to meet you. My name is Dennis. I'm a software engineer, and I'm interested in the mind, particularly within a Popperian and Deutschian epistemological framework. So I'm interested if you've learned anything from constructor theory about how the mind may work, or if you've had any insight on that.
So I think the answer is yes. I think so we haven't had an insight into that specific problem yet, but I think what I'm hoping is that, and what I think David also is interested in, is that the conceptual tools that constructor theory provides will allow you to tackle this problem in a radically different way. So the stage is just a hope, but I think there are reasons to expect that. And the main reason is that when you discuss, the mind in a sense is an entity that creates a particular kind of information, which you can think of as a resilient kind of information that also has causal power on the environment. And this is something that you can call knowledge.
Right.
That's the term that I think David and I also use to refer to that. And this particular kind of information in constructor theory can be characterized in an objective way. So you can talk about it as a copyable set of states with other specific information theoretic properties that I can then list, if you like. But I think the important thing is that you can characterize what knowledge is in terms of possible tasks without ever referring to subjective, scale-dependent, approximative concepts. And this is nice because usually in the theories of how knowledge is created, you get a lot of these, sometimes some stochastic sort of approaches. Other times you have some subjective ways of defining minds and things like that. And it's very hard to have an objective handle on these concepts. And that's problematic because for scientists like me, it's important to have a way of objectively describing or handling concepts even before ever creating a theory about them. So the hope is that once you have this concept available, you can then make a theory of the kind of physical objects that can create knowledge, like, for example, minds, or even, the other thing that creates knowledge is natural selection, which creates it in a much less efficient way. But these are the only two things that we know of in the universe that can create this kind of information. And so the theory doesn't exist yet, but I think so the conceptual tools that constructor theory provides will be very useful to develop on. And so there are also applications to, I think, AI and AGI. So and David is very interested in this kind of stuff. I'm also quite interested, and of course, this is not my main focus because I'm a physicist. I think this will. I'm hoping that someone in the field of AGI will notice this kind of comments and the concepts, and they will use them. And you already see that there are some people in that field who are trying to get away from the standard way of thinking about about learning and machine learning and things like that. There's Judea Pearl, who has this nice theory about counterfactuals, which is trying to get away with standard concepts, away from the standard concepts. So I think there is a need for these concepts, and hopefully constructor theory will provide some.
Right on. Thank you.
Yeah.
Amazing. Hey, Chiara, I'm realizing we're now 1 minute past the hour. We have 3 more questions. I'm not sure how you're doing on time.
I think I can take 3 more questions. Yeah, it's fine. Absolutely.
Yeah. Okay, lovely. I know those folks will be very happy. Okay, then without further ado, Yasha, your question is next. And I'm going to post a little bit more info on those salons here in the chat for those of you who have to jump off, and for those of for you whom it was the first time for joining. But for now, we have Yasha. Hi, Yasha.
Hi, I'm Yasha Bach. I'm an AGI researcher. I'm quite interested in David's and your theories, but I don't yet understand how constructor theory goes beyond constructive mathematics. That is, how can it compute things that a finite state machine, for instance, cannot compute in principle? I don't think that recreating yourself is an issue. This a program that reproduces its own source code is basically, it's called a quine, and it's a hobby that computer scientists have had successfully for quite some time. And so I didn't understand your metaphor of a 3D printer for the constructor in this sense. I do understand that you can take the constructor theory as a methodological approach that basically puts computer science in a slightly different hierarchy, but I don't see an ontological difference, and I don't understand the ontological statement that you and David are making when you say that you can compute things that other computers cannot.
Right. So the statement isn't of. So I think that was part of the motivation, and in a way, it's von Neumann's statement, and I'm just repeating what he said. So I'm more or less parroting someone that was already ahead of, even biologists in a sense. I think the point that von Neumann made, which is somewhat motivating the whole idea of a constructor, which should be a more general machine than a Turing machine, is that if you take a Turing machine, yes, you can have programs inside the Turing machine that can self-replicate, or you can have, the Turing machine simulating with a specific program the behavior of a cell that's self-reproducing. But there is no instruction you can put in the Turing machine that would get the Turing machine to create a replica of itself out of elementary materials, simply because the Turing machine doesn't even have the tools to do that, in a sense, right? So you would need arms to assemble the keyboard. If you're thinking of a modern Turing machine, you would need your computer to be augmented with a number of other working arms that or various tools that you would.
So this is about the substrate.
Say again?
It's about the substrate, in other words. So of course, if you are in a virtual world, you can create another virtual world that has the same properties as the virtual world. But
yes, there's no space in the Turing machine model. The only thing that the Turing machine can operate on is its tape. And there's no way that the Turing machine can create on its tape a new instance of itself. It doesn't even work. So if you think of the Turing machine physically, it just doesn't, so it's not possible for this to occur.
Well, there is no space. Space is not computable. What we observe is a set of locations and trajectories that information can take. That is what physics is about. And the space is something that exists in the limit when you look at too many of these locations to count and too many trajectories to count. Then you get to a space. But you can see that there are singularities in this space that are unavoidable. So space itself is not mathematically consistent. There can be space that works exactly like the space that you and me observe inside of a Turing machine.
No, but I think I'm now thinking of just the discretized model that can support the Turing machine. So I'm not thinking of some exotic physical theory. I'm just thinking of the discretized model of classical physics that within which you can define the model of the Turing machine. So the program that's, this program that can self-reproduce within the Turing machine, it's not really performing self-reproduction in the way that cells do, because it's using the error correction mechanism that's already within the Turing machine, and it's using a lot of other bits of the environment in which it is self-reproducing, which don't exist, let's say, in the biosphere when you're trying to look at what happens when a cell self-reproduces. So it's conceptually different from the self-reproduction that occurs in a cell. And I think von Neumann was interested in that. On top of it, von Neumann was really just talking about the Turing machine as a whole. So I wasn't interested in a specific subpart of it being able to, let's say, replicate. It was interested in the question, I define a task which is self-reproduction. Can the Turing machine execute it? And the answer is on itself. So there are different ways of self-reproducing. You can either have an entity look at its various details and then try to reassemble itself out of raw materials directly by inspection. But that's very prone to errors. And then, of course, there's the von Neumann logic, which is the correct one for high accuracy self-reproduction, which is that you have like a description of the whole architecture, basically DNA. And then that thing gets copied bit by bit. And then the initial entity that's self-reproducing executes that program in order to create a new instance of itself. And the Turing machine doesn't have the space for this kind of stuff. It just does not logically support this type of instruction. At best, it can do something on its tape, and that won't include creating a new Turing machine on its tape. That's not part of the Turing machine architecture. Von Neumann has a nice article on this. It's dated 1950 or something, and it's very nice. So I can send it to you if you want.
Yes, please. Thank you very much.
It's not something that David and I claim. In a sense, constructor theory is just taking the motivation to go beyond quantum computing, to have a theory about these machines that can act on more general transformations that are not just computations. And this is all what that reference to von Neumann was intended to achieve. Mm-hmm. I hope it didn't kind of confuse too much.
It didn't confuse, but I'm not yet sure about the answer. But thank you very much for your effort.
Yeah, no worries. Thanks for the question.
Thank you.
All right. Well, maybe we can find the paper and share it even in the chat.
Yes, I can send it to you if I find it later.
That's amazing. Thank you. Next one up, we have Ted Howard. Ted, I'll unmute you. Hi, Ted.
Thanks, Alison. Look, what is the role in constructor? Hi. What's the role in constructor theory for fundamental uncertainty? I heard you. I was interested in Jesse's response and Josh's question. They're both aspects of what I'm pointing at. You seem to be coming from the idea that you can have something which is tightly constrained that can approximate causality. But what if the universe we live in is constructed from infinities, and if Garrett Lissy has something in the idea that what we see as order is something that falls out of the symmetries that are allowed in infinities, when the symmetries are only like collector states where things tend to modulate, but actually all infinities are allowed, or any instance of an infinity is allowed, then you're dealing with something that's fundamentally uncertain. And the order that we have is an approximation. So we're back to uncertainties. Does constructor theory allow for that sort of approach, or is it where the constructors are themselves fundamentally uncertain?
Yes, I think the way in which uncertainty can come into physics, so there are several ways. So one is the one you mentioned. The other one is, of course, through quantum theory. And I think the key here is that let's take, a theory with infinity, for example, quantum field theory or field theory in classical physics has lots of infinities there. But you can still define within that theory a set of possible transformations. And so that doesn't mean that all the states of that theory, when transformed into one another, are free of uncertainty or free of infinities or free of whatever else. But you can distill a subset of the properties of physical systems that obey that theory, for which the statement a certain task is possible is valid and meaningful and consistent. So I think constructor theory is aiming to provide constraints on physical theories so that they must be expressible, at least in part, through these statements about possible and impossible tasks. If they cannot be expressed in terms of possible and impossible tasks, then they don't obey constructor theory, so they would be somewhat ruled out from the constructor theoretic picture of the world. It could be that constructor theory is wrong and those other theories are correct. And in which case, it would be nice to find an experiment that could tell those two things apart. But I wouldn't, in the specific case you were referring to, I wouldn't know what experiment one could think of. But what I'm trying to say is that we are still within, the classical physics dialogue in a way, because constructor theory is just proposing a certain understanding or explanation of the world, and it could be that it's just wrong. in that case, in which case, we should switch to something else at some point. But we are not yet at the point where you can make a prediction and test it against something else.
It seems to me that our human brains are heavily biased by the fact that evolution most heavily selects for things that respond quickly under urgency. So we're heavily biased to simplify things. So we have this bias that likes to take us back to binaries and take us away from infinities and uncertainties. And that seems to be driving the direction that you're going in.
So it's possible still, then my first answer applies here, because the first part of the answer, in the sense that you can still reconcile a structure which is highly counterintuitive, like, let's say, the structural field theory, where you have infinities popping up everywhere, with the presence of the definition of an information variable, which is a completely discrete and finite set of states. So it's possible to construct a model that complies to this intuitive, discrete type of structure within a theory that still allows for infinities and continuum and so on, such as field theory. In other words, what we are saying is compatible with certain kinds of infinities, and so I don't see them in contradiction necessarily. It's just that the statements I'm making at the level of the possible and impossible tasks should be seen as the fundamental explanations for everything else, and not the other way around.
Yeah, it smacks of bias to me, but yeah, I can see why the bias is there.
Well,
as an evolutionary biologist, that's my background.
I suppose all things are biased. I mean, it's impossible to approach any problem without a bias. Everyone has a bias. It's just the background knowledge you have. So in a sense, I suppose, the whole of quantum theory is biased, or the whole of Newtonian is biased.
Thank you.
All right, thank you so much. And then we have Dan Gershowitz. Dan, I'm going to unmute you now. Let's see. Harder to do than I thought. Sometimes it takes forever to unmute someone. Oh, now I muted him. Then I muted him again. Now,
Hello.
Hi.
Thank you for taking the time, Chiara. Really appreciate it. I'm Dan, and for the last question, I guess, I'm really curious about what constructor theory has to say about observer-independent facts. There's a paper I think I just posted to the chat about the inability for modern physics to say certain things are objective. And it seems from what we've been talking about with probabilities and what I know about how knowledge and constructor theory are tied together, that in a sense it's a purely local or purely subjective approach, and that would it be fair to say you wouldn't be able to say, you wouldn't be able to make purely objective claims using constructor theory?
Right. So I think as I was saying earlier in reply to another question, the take in constructor theory, which is actually, I would say, the take in all other laws of physics we have, is that the most fundamental entities are actually objective and they are observant and independent. So I know that there is, let's say, even in quantum theory, there is often a narrative about quantum theory that says that things are dependent on who is observing what. For example, there is this famous title of a famous paper saying, is the flux there if nobody looks? So this is referring to the fact that when you have a quantum superposition of various values, there comes a moment where someone is performing an observation of that superposition, and then suddenly one of the various values become real for that observer, or something like that. Now, I think that's not, so this is an interpretation of quantum theory, which seems to me is not correct. And if you look at quantum theory properly, you take it seriously, and you're not adding other assumptions on top. Quantum theory just tells you that there is an objective reality made of the quantum wave functions, and then the measurement is just another quantum interaction, and you can describe it all nicely and consistently. And every statement you can make about entanglement, superpositions, outcomes, probabilities, all of these things are objective. And they are observer independent in the sense that having fixed a coordinate system, everyone, and even people sitting in different coordinate systems will agree on what's happening, modulo, of course, proper, translating properly between their own way of predicting and the way of predicting of a different observer. But the fact that, let's say, according to relativity, there can be, you can compute the probabilities of the outcomes of certain experiments in different coordinate systems doesn't invalidate the statement that the output that you get out of these calculations are referring to objective facts, and there's just one truth, one fact of truth of the matter that refers to the physical system that you are describing. And I think this is true in all physical theories we have. In constructor theory is the same. And to convince you of this, even if you don't want to go into constructor theory details, you can just take the conservation of energy, which is an example of a principle that has the same logic as constructor theory's principle, and is well known because it's just already part of the structure of physics. When you say that energy is conserved in a certain physical theory, that is an objective statement. It doesn't depend on whether there are observers around, or it doesn't depend on the particular way of looking at the system in question. It is just a fact, and it just says that if you've got the system with a certain energy, in order to change it, you have to bring the energy from somewhere else or take it away move it to some other location in space-time. And that's it. And I think the spirit of the logic behind all of the statements in constructor theory is very similar to the logic of the conservation of energy. So we are hoping that this approach is very much objective. And I would be very wary of statements about observer dependence, because although it's true that there are some quantities that, in relativity you can express with different values in different reference frames or in different coordinate systems, that's one fact. But that isn't in contradiction with the fact that there are objective entities in the theory of relativity, which are, the symmetries of the laws and various other things that are actually the elements that we're using to describe physical reality. So I very much support, and I think I'm hoping constructor theory does the same. I support the view that, let's say, science should provide some objective view of reality.
All right, thank you so much.
Even observers should be describable fully within the theory. That's one lesson that we got from quantum theory. Even macroscopic observers like us can be included in the laws of quantum theory, let's say, and I think constructor theory also can be applied in a sense to entities like macroscopic observers.
Okay, thank you so much. I forgot one question by Harrison from earlier. Maybe he could, if you don't mind, he could ask the question, and then you can decide either to take it or to do, and maybe you could weave that into a few final remarks of kind of like what's happening now. Is there a book coming out? I think I said that in the introduction, but so that we have like a little roundup of how we can find out more about you. And I'll unmute Harrison, and I think the question is really worth it. Okay, let's see. Harrison, you're unmuted.
Hi, Chiara. Thanks so much for coming on. I've wanted to learn more about this stuff for a while, and I think this idea that you have in your program of taking the sort of like possibility statements and making them sort of the primaries and the dynamical laws, and making them, the epiphenomena of those primaries rather than the reverse as we see today, is really cool. That being said, the primary content of like dynamical theory isn't just like there's a dynamical law, but like what the mathematical statement of those laws like is. And so I guess this is a question about like where you are in your research program. Can you give us a sense of what the mathematical statement of a constructor theory or several different constructor theories would look like, in the same way that like Newtonian mechanics is an example of a compelling mathematical statement of this sort of like state and continuous transition function idea. Like, what would the math of like, you know, what it is possible to construct look like?
That's a nice question. I think I started to mention something earlier in reply to another question. And I think it's nice that you're kind of asking this, because the way in which the theory looks is very different from dynamical laws. It doesn't have dynamical laws directly, and the basic formal objects are tasks, and these tasks are basically, if I can use some jargon, they are sets of states, input-output states. And so being sets, you can think of them as being composable with one another. So there's an algebra of these tasks. So the current way in which we're presenting our results is based on set theory combined with algebraic tools that describe the properties of the algebra of tasks. And then there's a combination of there are some rules that say how possible and impossible tasks compose together. So there is also a function, which is this function that tells you whether a task is possible or impossible. There's like a label that you put on top of these sets. And I think these are very rudimentary mathematical tools, if you like. So, you know, if I've got, as I said, some collaborators who are trying to rephrase these statements and results that we have in terms of more sophisticated maths, which is basically category theory. So I think if you want to know what a constructor theory of, you know, fully fledged theory of constructors would look like, fully fledged constructor theory will look like in the future, it should be expressed with, so it seems like the natural way of expressing it is category theory. Having said that, I think the current results are mathematically rich in themselves, and I think it's possible to see this even with this set theory approach that we currently have. And in fact, you know, if anyone has suggestions about, you know, different tools that one could use, it would be welcomed, you know, because we're really exploring something very different from the standard dynamical laws that you have in physics. And although these dynamical laws are compatible with what we say, the kind of statements and the proofs that we make are you know, just follow a different formal structure. So happy to get suggestions and from anyone in the audience.
I think you got one already in the chat. And is there a way in which people could follow up with your work specifically that I may have not mentioned yet, or is there a way where we can?
My email is on the internet, and I'm very happy. There's constructortheory.org, which is the platform where we kind of post our results. But also, as I said, if anyone wants to ask more questions, you can Google me, and there is an email address. So I'm very happy to reply to further questions. And I will find the Neumann article and maybe send it to you, and you can, is it possible to send it back to?
Yes, we have an email list, yes.
Yeah. Okay, excellent.
Fantastic. Hey, Chiara, I can't thank you enough. I think, it was like a very, very well enjoyed salon by everyone. Thank you so much for making the time so spontaneously. I can't wait to get the book. Maybe we can have you back on when the book is out. And for now, thank you so much for making time. I'm going to follow up with you about the video, and then I'll follow up with all of you guys to share the video relevant links. For now, I'm going to open up breakout rooms. If people want to continue the discussion informally, I won't be there. So please be nice to each other and maybe introduce yourselves in the chat. And the breakout room should be open. And I hope to see many of you again next Thursday for Anders Sandberg from the Future of Humanity Institute at Oxford for another salon. Thank you so much, Chiara, from all of us. It was really fantastic to have you.
Thank you so much. Thank you, everyone, for the questions.
Bye.
Take care. Bye.